In this second video from Chapter 4, I'm going to go ahead and continue with my discussion of hydrogen bonding. So I'd like to talk about the issue of compound solubility being a function of hydrogen bonding. So when we're looking at whether substances will dissolve in each other, one of the most important sayings that we use is this very simple one: like dissolves like. And what we find then is that compounds that can make hydrogen bonds tend to be somewhat soluble in water. Or more simply, compounds which are polar tend to dissolve in or mix with other compounds which are polar. And vice versa, things which are nonpolar tend to mix well with other things which are nonpolar. So what this means is that many compounds which can make hydrogen bonds are likely to be soluble in water. And as we get a little bit further in the class, we'll explore that a little bit more deeply when we talk about organic molecules. And the final intermolecular force I'd like to discuss are the London dispersion forces. And in general, they are the weakest of the intermolecular forces, but they're also the most universal because all molecules can experience these. Molecules without a dipole moment and those with one. Although it's going to be most important for molecules which do not have a dipole moment. In other words, molecules that are not polar. So all molecules can be thought of as having electrons that are flowing across their entire structure. And what happens is, as those electrons move about from one place to another, certain parts of the molecule can become negative, albeit temporarily. And as those sections of the molecules become partially negative, other sections of the molecules become partially positive. Now, when that happens, nearby molecules will react to that. So if they're suddenly being approached with a negative charge, that can chase electrons away from nearby molecules and cause those areas to have a partial positive charge. And that's what we mean by an induced dipole. One molecule causes a neighbor to suddenly have a slight dipole, or partial positive and partial negative charges. And so when those partial charges suddenly occur, there will be an attraction between the positive and the negative of two different molecules. But then, almost an instant later, the electrons flow back to their original positions and the dipole suddenly disappears. And that makes this a very short-lived kind of attraction. Now, where we start to see these as being important is with longer molecules that have large surface areas. And in particular, later on in the course, when we start talking about fats and lipids, this becomes very significant. So here we're looking at two methane molecules. CH4 is nonpolar, and so there's not normally going to be positive or negative regions with these molecules. However, as electrons move about through the molecule, it is possible that these electrons could, for a moment, tend to be more favoring the left side of the molecule, as we're seeing in this picture. And as the electrons favor the left, the right side becomes positive. Well, when that happens, this molecule can react. Its electrons are attracted to the positives of the next door molecule, and so we have a temporary attraction here. And when these electrons come back, the molecule is back to being neutral. These electrons go back to their place, and the attraction disappears. So this is a very, very small attraction for CH4 molecules. Let's go ahead, though, and see what could happen if we had molecules that are larger. So what I'd like to do here is I want to go back to looking at methane. So let's say that we represented a methane molecule here with a small sphere. And so within there we have the carbon atom in the center and the four hydrogens kind of pointing out in different directions. And then what I'd like to do is take that and make another copy of it. And let's see how they approach one another. Now, you see, there's very little point of contact between these two molecules. They're surface areas relative to each other, their contacts on those surface areas is very, very small. So you'll notice they can just kind of meet right at tangents here. So as, say, for example, we get some partial negative charges in here. So like on this side, let's say we're partially positive over here. And that makes this side negative. Those electrons chase away the electrons on this methane, and that makes this side positive as this side becomes negative. There's very, very few points of contact between those kinds of shapes. And so with methane, we do expect there to be London forces, but because of that small contact point, they're going to be very, very weak. Let me compare that, say, to a molecule that's related to that, but instead of having just one carbon and 4 hydrogens, let's say it's a much larger molecule here. And so I'm going to represent it here as something like this. Okay, so this is a molecule which is much wider, a much larger surface area. And let's say we have another one nearby that has a similar shape. And so what I would like to be able to show here is, let me take this guy right here and move him. Well, they're not exactly the same size, but they're close enough. Is with a molecule that's much larger, so say, 14 carbons, for example, let's say that we get some negatives over here. So electrons suddenly come over to here, and this region is negative, and so we're negative over here, and then this region becomes positive. And that will cause this region here to become positive. So there might be an attraction here, but then over here something else could happen. So maybe this becomes positive over here because the electrons were chased away, and then electrons would want to come here, and this would be negative. So they'd be at a point of attraction there. And then you see, I'm going to leave out those little deltas for right now. What we might find are all these different points at which these attractions can occur. And this is much different, as I said, than just like these little tiny molecules like methane, where there's very few points that they can interact. And so with large molecules like this, we commonly experience strong London dispersion forces, much stronger than in methane. But then what happens? As I mentioned, over time, these forces are temporary. So suddenly they go away. But maybe these forces are still lasting, and when they start to go away, some new forces form over here. So when there's large molecules, there's almost always some point of attraction going on at some place or another. Oops, just got rid of a whole molecule. So if they are temporary, they come and they go. So now that we've seen all three of our intermolecular forces, let's go ahead and compare them. So general order of strength, and general means on average, so to speak. It's not always going to be true, but it's going to be generally true for molecules of about the same size. We generally find that hydrogen bonding is the strongest of the intermolecular forces, and then dipole-dipole is the next strongest, and then London dispersion forces are the weakest. All of these are weaker than regular bonding. So, for example, ionic bonds we already talked about, they're extremely strong, and then covalent bonds are also quite strong, but not as strong as ionic. Both of those are much stronger than any of these intermolecular forces. So if we're trying to compare these, what we only are interested in is the strongest force present, because all molecules, for example, have London forces. So if a molecule has hydrogen bonding and London forces, we don't really care about the London forces so much as the hydrogen bonding. under most cases. So you want to locate what is the strongest force that each molecule possesses first. And this is important because it will allow us to compare how high a melting point is of one compound compared to another. The same thing with boiling points. And for example, compounds with very, very high melting points tend to be solids at room temperature, high melting points and high boiling points, whereas compounds with very low melting points and very low boiling points tend to be gases. So let's make a comparison here. So methane, as we saw, the only forces it experiences are London forces. The boiling point of methane, this is just natural gas here, is negative 162 degrees Celsius. And its melting point is negative 183 Celsius. So let's be very clear that we understand what this means. This boils at negative 162 Celsius. Room temperature is about 25 degrees Celsius. So what does that mean? 25 Celsius is a much higher temperature than negative 162. So this goes from a liquid to a gas at negative 162. So that means at 25 Celsius it is a gas. In between the boiling point and the melting point, the substance is a liquid. And then the melting point, which is also called the freezing point, anything lower than this is where we have a solid. So to get methane to be a solid, you have to go all the way down to below negative 183 degrees Celsius. Let's compare this with water. So all molecules have London forces, but water also has dipole-dipole forces, and it has hydrogen bonding. So we only worry about the strongest force, hydrogen bonding. Water is an especially important molecule because it's so small, and yet it has an incredibly high boiling point. So room temperature, again, is 25 Celsius. So what do we expect water to be at room temperature? Well, it's above the melting point, but below the boiling point, so this means we would expect water to be a liquid at room temperature, which it is indeed. So, stronger intermolecular forces for molecules of a similar size ultimately mean they're going to have higher boiling points and melting points compared to molecules with very weak forces like London forces. What if we compare molecules that are of a less similar size? So this is propane, and this is butane. Their only real difference here, if you compare them, is that this one has one more carbon atom and two more hydrogen atoms than this compound does. What does that do? Well, larger molecules generally experience stronger forces. And so that's why butane boils at about 0 Celsius, whereas propane boils at negative 42 Celsius. What state are both of these at room temperature? 25 degrees Celsius is well above the boiling point of both of these, so these are both gases at room temperature. Let me compare that to octane, which now has 8 carbon atoms and many more hydrogens than propane or butane. And now you'll notice that the boiling point has gone up substantially. So the larger it gets, that's what we expect. What is octane at room temperature? Well, room temperature is 25, so that's between the boiling point and the melting point. Octane should be a liquid. So what is the strongest intermolecular force that we see for each of these molecules? Some people might say, what is the most important intermolecular force? So we always want to go in order of asking ourselves, first, can a compound make hydrogen bonds? If the answer to that is no, we ask, does it at least have a dipole moment? And if we say yes, then it's the dipole-dipole force. And if we answer no to both of those, then London forces are the only thing that we have. So if the molecules aren't familiar, you'll always want to start by drawing in Lewis structures of these. So let me do that. Let me draw Lewis structures of these as I go. So here we have ammonia. And we are only talking about whether something can make hydrogen bonds with itself right now. We're not dealing with water at this point. We're only talking about pure substance, pure ammonia. So nitrogen has a hydrogen on the phone, so there's a hydrogen bonded to the nitrogen, and nitrogen has a lone pair. This means that this can hydrogen bond. So hydrogen bonding is the most important, the strongest force this has. We don't even worry about the others. This compound here is called ethane, very similar to the propane and butane and octane that I just showed you on the previous slide. This is what we call a hydrocarbon. It contains only carbon and hydrogen, and these will be the subject of chapter 10. Okay, so first of all, can this hydrogen bond? There are hydrogens, but none of them are bonded to F, O, or N, and there are no F, O, or N atoms. So hydrogen bonding is out of the question. Does this have a dipole moment, or can we say it's polar? Well, carbon and carbon share electrons equally, and carbon and hydrogen share almost equally. Remember, we've said carbon hydrogens don't tend to have are non-polar covalent bonds. So therefore, everybody's sharing equally here. So this molecule is non-polar. And if it's non-polar, that means the only force that we have are the London dispersion forces. So that's the only force that this has. Bromine. We only have two atoms here. It's a linear kind of a structure. And since these atoms are identical, they are going to share electrons equally. I didn't ask myself if there was hydrogen bonding. I didn't really need to because there are no hydrogen atoms here. This can't have a dipole moment because the electrons aren't going to want to go more to the right or to the left. They will share equally. So this is another non-polar molecule. And if it's non-polar, the only force we would expect to see are London dispersion forces. Now it's interesting, though, that this molecule, bromine, is a liquid at room temperature, and ethane over here is a gas at room temperature. These atoms are much larger, and so it's partly owing to that we would expect that this molecule, even though the attractions are weak, it's going to have higher boiling points than, say, for say for ethane. Okay, and then finally here we have a compound called trifluoromethane. My covalent bonds aren't very nice there. They're adequate, though. Okay. And of course you would be going through the rules that you learned in Chapter 3 to draw this. But you'll learn some shortcuts later on. Okay. So we have a central atom here, which is bonded to 3 fluorines and a hydrogen. There is a fluorine and there is a hydrogen, but the hydrogen is bonded to carbon. So this cannot hydrogen bond. The hydrogen must be on the phone, F, O, or N. So no hydrogen bonding. Is there a dipole moment? Well, the electrons are being pulled up and down, so that kind of cancels. But they're also being pulled right, and there's nothing to cancel in that direction. So therefore, this molecule is polar. So it doesn't have hydrogen bonding, but it has the next best thing, which are the dipole-dipole forces. And that will end my discussion on intermolecular forces. The rest of the chapter I'm going to be looking at energy-related topics, and we're not going to go too much into detail on these. So the first of these that I'd like to address is called specific heat. And specific heat is defined as the amount of heat energy in either calories or joules that you need to raise the temperature of 1 gram of a substance by 1 degree Celsius. Let me correct what I just said. It is the amount of heat energy in calories or joules, but the units of specific heat are calories over gram times degree Celsius, or joules over grams times degree Celsius. Now, if you think back to the wording of this, we actually already talked about this terminology with water. We said 1 calorie is the amount of energy that you need to raise the temperature of 1 gram of water by 1 degree Celsius. So its specific heat is going to be 1, as I'll show you in just a second. But the most important thing I want you to know is this idea right here. The larger the specific heat, the less its temperature will change when it absorbs a certain amount of energy. Okay? So in other words, when something has a high specific heat, you have to put a large amount of energy in to raise its temperature. Whereas something with small specific heat, if you put that same energy in, its temperature will go way up. This is assuming we're comparing the same mass of a substance. Okay. So again, there's that definition there for calories. We said specific heat of water, 1 calorie over grams times Celsius. So 1 calorie of heat has to be added to increase the temperature of 1 gram of water by 1 degree Celsius. If you add 2 calories, what can that do? If you add 2 calories, that could raise 1 gram of water by 2 degrees Celsius, or it could raise 2 grams of water by 1 degree Celsius. So what I'd just like to do here then is just to compare some of these. So we have 2 different sets of units here, calories per gram degree Celsius or joules per gram degree Celsius. I don't want to use calories per gram degree Celsius. Let's just ignore those for right now. So we're only going to compare this column and this column. And what compound here has the highest specific heat? Well, at 4.18, it is liquid water. Liquid water has a very high specific heat. You have to put a lot of energy in it for its temperature to go up. Think about this when you're trying to boil water, say to make spaghetti on the oven. It doesn't just suddenly get hot. It takes a lot of time for that water's temperature to go up. On the other hand, let's say you had an aluminum or a copper pot, and you were just trying to heat that pot empty without the water. Copper has a much, much lower specific heat, which means that it will heat up very, very readily. You don't need to add a lot of heat to get its temperature to go up. Aluminum has a specific heat that's more than twice as much as copper, so you need twice as much heat to raise the same amount by the same temperature there. And when we get down here to the very, very low values, we have things like gold. It has an extremely low specific heat. So if you just leave a piece of gold out in the sun, its temperature will go up rather rapidly, we would expect on a warm day. One important point here, and that is that each of the different states of matter, liquid, gas, or solid, would have their own specific heats. So we're not going to do any calculations involving these. The next thing I want to look at that's related to this are phase changes, also sometimes called changes of state. And this is just the terminology we use when something goes from a solid to a liquid, or liquid to a solid to a gas. Most of these terms should already be familiar to you, but let's go ahead and go over them anyway, and you'll want to be sure you know these. So when something goes from a solid to a liquid, just think of water. So solid water is ice. When it becomes a liquid, we say the ice is melting. So not a very difficult term, one you already know. And what is the opposite of melting? Going from a liquid to a solid? That is freezing. Liquid to gas can be kind of complicated, and gas to liquid is one that you probably are familiar with. That's called condensation. You know, if you leave, for example, a very cold soda can out on a table, the water that's in the air, the water vapor, condenses on the cold container and makes liquid. So that's just what we experienced there. So it's condensation. Going from liquid to gas, the terminology is different. There's actually 3 words here we could use. Vaporization is very general and very generic, and probably the best term to use. It just means liquid to gas, and that's it. Evaporation means that a liquid is changing to a gas, but it doesn't have to be at its boiling temperature. If you spill water, for example, out on concrete on a day that's even slightly warm, you know that that water will evaporate, but you'll never see it suddenly start to form bubbles and steam out and boil. It doesn't do that. So evaporation is liquid to gas, but it's below the boiling temperature. Boiling is what occurs when you go from a liquid to a gas at or above the boiling temperature. And I don't want to get too much into the theory of why that happens, but it has to do with bubbles and gas pressure. And below the boiling point, you can't form bubbles that will survive going up to the surface. They get crushed by the liquid above them, so to speak, and therefore we don't experience boiling. So much more complicated than we're going to go into, but just use the term vaporization. Solid to gas and gas to solid are things that we don't usually see quite as often. If a gas becomes a solid without going through liquid on the way, we call that deposition. And if something goes from a solid to a gas, that is called sublimation. The most common example of sublimation is dry ice. Dry ice is solid carbon dioxide. If you leave solid carbon dioxide out, it will just sublimate and become gaseous carbon dioxide. It only becomes a liquid under much higher pressures. So that's what we see. Even ice cubes will sublimate, because if you leave ice in a freezer long enough, especially if you leave them in old-fashioned plastic ice cube trays, you'll notice that the cubes get smaller and smaller. That is water sublimating from the ice as it becomes a vapor. And I want to then take the main theme of the chapter, which was energy, and add that into phase changes so that we're combining these together. Okay. So a couple terms you really need to know. Exothermic. This will come up a lot in the next chapter. Exo means out, outside. Therm means heat. So out heat. This is a process that gives off more energy, specifically more heat, than it consumes. All the types of reactions which we'll talk about, called combustions later on, are exothermic. And combustions are the same idea as burning. So if you burn a candle, that's exothermic. You have to initially start the flame, but once it's going, it will give off more heat than it takes in. The opposite of exothermic is endothermic. So it takes more heat into it than it gives off. I want you to think about it this way. Let's say you're holding a test tube in your hand, and there's an exothermic reaction in the test tube. It's giving off more heat than it consumes, so how are you going to feel if you're holding the test tube? It's giving off more heat, so that means your hand will feel hot. On the other hand, if you're holding a test tube that has an endothermic reaction going on inside of it, your hand is going to feel cold because it is taking heat out of your hand and putting it into the reaction going on in the tube. So essentially any phase change which causes molecules to have more energy is endothermic, specifically kinetic energy. In other words, you have to keep adding energy in to supply that kinetic energy so that the molecules can move. So a good example of this would be melting ice cubes. Ice cubes are solids. the water molecules are mostly locked in place. If we want to give them more motion so that those water molecules can float over each other, they become a liquid, you have to add energy. That energy could be from a stove or just from the air. Just putting ice cubes out on an ordinary day will be enough energy to melt those ice cubes. So that would be endothermic. On the other hand, if you tried to do the opposite and freeze the ice cubes, that would be an exothermic change. It's like you're taking heat out. And so you can think of it this way. When you freeze water to ice, you are removing heat. And if you feel the back of a freezer, you'll notice that they are generally quite warm. Partly the electricity, and it's also that heat that has to be removed and dissipated for those things to occur. So let's look at the change between melting and freezing. What do these have in common? They take place at the same temperature. That's an important thing to know. It's just if you're adding energy, you're going from the solid to the liquid, that would be melting. And if you're taking energy away, it would be freezing. And the temperature at which this occurs is called the melting point or the freezing point. Either term is acceptable. So the amount of energy that you need to melt 1 gram of a substance is the heat of fusion. And so for water, you don't need to memorize this value, but it's 79.7 calories per gram. So if you have 1 gram of ice, putting in 79.7 calories of heat will cause it to melt, so long as the ice is at 0 degrees Celsius. If it's below 0 degrees Celsius, you'd have to add heat to get it to the melting temperature, and then when you add this amount, it will melt. So that's called the heat of fusion. What if we want to go from liquid to gas? Well, if this is water, first you have to heat it up until it's at the boiling point. That's 100 degrees Celsius. And so we call this here the heat of vaporization, the energy that you need to go from a liquid at the boiling point to a gas at the boiling point. So it has to be already at the boiling temperature. And so what is it for water? It is a huge number. It is 540 calories per gram. Compared, if we go back just a couple slides, to the heat of fusion, that was about 80. So this is vastly more. So what this is telling us is we have to put a huge amount of energy in order to vaporize something. Why? What are you doing here? What is holding the water molecules together? We already talked about that. It's hydrogen bonding. To make a liquid become a gas, you have to break all those intermolecular forces. You're not breaking the bonds. This is still H2O. You still see 2 hydrogens and an O, 2 hydrogens and an O. You haven't done a chemical change, but what you have done is separated them. And so this requires a huge amount of energy to ultimately break up the intermolecular forces. And that's what you're doing when you're vaporizing. When the process goes the other way, the same amount of energy goes back. So when this condenses, it releases that energy. This is very important in a medical context when we talk about different kinds of burns. A burn from water at 100 degrees Celsius is not, liquid water, is not going to be nearly as bad as a burn from steam at 100 degrees Celsius. So a steam burn is generally far worse. And let me explain why. Well, first, let's say you're just burned with 100 degree Celsius liquid water. That's bad. Your skin, let's say it's about 35 degrees Celsius. So as the 100 degrees Celsius water comes into contact with skin that's 35 degrees Celsius, the heat will flow from the higher temperature to the lower. So a lot of this heat is going to go straight into the skin until these become roughly the same temperature. This would, be, of course, not likely be the scenario if you're just getting splashed with it, but a lot of heat comes from that liquid right onto the skin. With a steam burn, on the other hand, what you have to imagine is it's already at 100 Celsius, but it's already had all the molecules separated. When you go from the gas to the liquid, it is exothermic. All that heat goes straight into the skin as it goes from steam to a liquid. At that point, it is still a liquid at 100 degrees Celsius, and it will still continue to damage the skin, giving off the heat until it lowers the temperature even further. I read an article recently about this, that the other problem with steam burns is that we expect that the steam can actually penetrate pores, at least until it condenses into a liquid. And this allows steam to travel to lower layers than just the epidermis of the skin, the outside of the skin. This can actually get into the dermis through the pores and cause damage at a much lower level. And so steam burns are particularly dangerous relative to just ordinary hot water burns. So you have to be extremely careful around steam. How do you treat steam burns or hot water burns? You don't add ice. That would be a general recipe for disaster, because that can numb it and you can actually end up with frostbite. You always want to have cold running water, and it needs to be cold running water that goes for a long time. As the water runs over the skin, it's like it takes the heat with it and helps to mitigate the damage to the skin. Just because it doesn't feel like it's burning anymore doesn't necessarily mean that that the damage has been stopped, because nerve damage could have been done in the process of the burning. So just running it with cold water and then eventually maybe room temperature water would be the best course of treatment in this kind of a scenario. That's it for Chapter 4. I'm going to go ahead and stop here. And in the next chapter, we will start to look at chemical reactions. We've just been looking at physical changes here, but what happens when we want to react these and make them into different substances? That's all going to be covered in Chapter 5. Thank you.